Have you ever wondered how a bridge can stretch for nearly 2 kilometers across open water and still hold thousands of cars every day? Bridges like the Golden Gate Bridge look almost impossibly thin for the weight they carry, yet they survive earthquakes, massive winds, and millions of vehicles. So how do engineers make something so strong using cables that look like strings? Today we're breaking down the brilliant engineering behind suspension bridges. At first glance, a suspension bridge looks simple. 2 towers, a road hanging in the air, and some cables. But in reality, it's one of the most elegant structural systems ever invented. The secret lies in how forces move through the structure. Every structure deals with 2 major forces: compression, which are squeezing forces, and tension, which are pulling forces. Most structures, like old stone arches, rely heavily on compression, but suspension bridges flip this idea on its head. Instead of pushing forces down through solid material, they hang the entire roadway from cables under tension. Think of it like a giant hammock, but for cars. Let's break down the 4 key components. First, the towers. The towers carry the entire load of the bridge vertically. They transfer all that weight down into the ground through compression. That's why bridge towers are usually built from massive steel or reinforced concrete. Then, we have the main cables. These are the most important parts. On the Golden Gate Bridge, for example, each main cable is about 90 centimeters thick and is made up of over 27,000 individual steel wires bundled together. These cables run over the tops of the towers and are anchored deep into the ground at both ends. They carry almost all the bridge's weight and tension. Next are the hangers. The vertical cables you see running all along the bridge are called suspenders or hangers. Their job is simple. They connect the main cable to the road deck, transferring the weight of the traffic and the deck itself upward to the main cables. Finally, there's the deck. This is the part cars actually drive on, but it's much more than just pavement. Engineers designed the deck to be stiff enough to resist twisting, especially in strong winds. And that particular detail became incredibly important after a very famous engineering failure. In 1940, the Tacoma Narrows Bridge in Washington state collapsed dramatically. Wind caused the bridge to enter a phenomenon called aeroelastic flutter, where the airflow created oscillations that just grew larger and larger. Eventually, the bridge tore itself apart. After that disaster, engineers learned a critical lesson. Aerodynamics must be a key part of bridge design. Modern bridges now use open truss decks, aerodynamic shapes, and extensive wind tunnel testing, all to prevent the same thing from ever happening again. So why choose a suspension bridge instead of another type? Because they are perfect for extremely long spans. When distances exceed about 1 kilometer, other designs become inefficient or even impossible to build. Suspension bridges distribute weight so efficiently that they can stretch across incredible distances. A modern example is the Akashi Kaiko Bridge in Japan. It has the longest central span in the world, nearly 2 full kilometers. What makes suspension bridges truly special is how simple physics creates massive strength. The roadway pulls down due to gravity. The cables pull sideways toward the anchors. The towers push straight down into the earth, and the anchors hold everything in place. When all of these forces balance perfectly, the entire structure becomes stable, flexible, and unbelievably strong. Next time you drive across a suspension bridge, look up at those cables. What might seem like a delicate web of steel is actually a masterpiece of engineering. It's a structure that turns gravity, tension, and balance into something powerful enough to hold an entire city's traffic. And it all just hangs by cables. Thanks for watching, and don't forget to subscribe for more engineering breakdowns.